In the previous lecture, we talked about superposition of waves, and that resulted in something called the standing waves. As an example, we discussed standing waves on a string, and we found that given a length L of the string, certain frequencies only were allowed for it to vibrate with. That is because the string, if it is of length L and tied at both ends, its ends could not move, and therefore, they were nodes, and the wavelength had to be such that the string did not move at these points at all. So, either you had half a wavelength on it or one full wavelength on it, and so on. On the other hand, we also considered situation where one end was fixed and the other end was free to vibrate. It is like if you take a long rope, hold it in your hands and move your hands up and down. In that case, we saw that either 1/4 of a wavelength could be excited or 3/4 of wavelength could be excited, and so on, and these gave the frequencies with which the string could vibrate. Exactly along the same lines, we can also now discuss the vibrations of an air column in a pipe. And let me explain what that means. What that means is, suppose I have a pipe. It could be open ended on both sides, or it could have a closed end on one side. An open end on the other. And the air inside it can vibrate. When air inside it vibrates, for example, when you see a flute being played, the air column inside is vibrating. What kind of frequencies can it vibrate at? Now, remember, air column vibration is described by, so vibration of an air column is described by pressure variation. And if you look at these two pipes, we have been discussing that the open end, the pressure would be the same as in the atmosphere. So, pressure variation at the ends would be 0. Whereas, in the middle it could be quite large. Similarly, for the open ended or the closed end pipe, on the right side delta P would not be 0, because the closed end out here, this wall, can withstand any pressure. On the other hand, the open end delta P will be 0. Let us go to the next slide and see what does that mean. So, if I consider the open ended pipe, delta P on two sides is 0, and it could be delta P is 0, and in between it could be non-zero if the air column is vibrating. This is exactly the same situation as that of a string. Remember, in a string, the displacement delta y at the ends was 0, and in the middle delta y was not 0, delta y or y the displacement. So, the string could vibrate in different modes and so on. In exactly the same manner, now if I look at this open ended pipe, and if I were to plot the variation of the pressure in the middle, it will be 0 at the ends, it could be large right at the center, or it could be 0 at the ends and a different kind of variation at the center. But you see, the change in pressure as a function of length is exactly the same as change of displacement of a string as a function of length on it, and therefore, their vibration frequency should be the same. Now, how do we deduce that? Recall that in the case of the pipe, I am going to write delta p, which would be described by, depending on how I choose my coordinates. So, I will take the left hand to be x equals 0 and the right hand to be x equals L, that is the length of the pipe, and delta p would be a sine of k x cosine of omega t or any different variations. I have chosen sine k x because this gives delta p to be 0 automatically at x equals 0. Now, I want delta p at x equals L also to be 0. So, before that I should point out this implies that delta p at x equals 0 is automatically 0, and this means that sine of k L is equal to 0 for at all times, and therefore, k is going to be n pi over L, exactly in the same manner as it was for the string. And therefore, I have for this open ended pipe, uniform pipe, one end I have taken to be at x equals 0, the other end at x equals L. Delta p is 0 here, delta pressure is 0 here, and it changes in the middle, and I have delta p as a function of x and t as given as some amplitude a of the pressure times sine k x cosine of omega t, and what we have deduced just now, because delta p at x equals L at all times is 0, this means sine k L at all times is 0. What it means is that k is n pi over L. K is nothing but 2 pi over lambda, which should be equal to n pi over L. I cancel pi on both sides and I get lambda equals 2L over n, and therefore, the frequency nu n is going to be equal to V over lambda. V is whatever it is, we have found this earlier, square root of b over density or gamma is square root of b over density, but important thing is going to be n V over 2L. So, the frequencies are nu 1, which is V over 2L, nu 2, which is 2 V over 2L, and so on. So, this air column can vibrate as frequencies which are multiples, integer multiples of V over 2L. These are, by the way, known as, in the case of strings as well as air columns, the frequencies which are given as n V over 2L are known as harmonics. So, n equals 1 is first harmonic, n equals 2 is second harmonic, and so on. N equals 3 will be third, n equals 4 will be fourth harmonic, and so on. the frequency V over 2L. Notice that the expression is the same as in this case of string, is known as the fundamental frequency. So, whether I have a string of length L, where the displacement is 0 at the ends, or I have a pipe where the pressure change is 0 at the ends. So, the boundary conditions, what happens at the boundary of this medium, whether it is a string or a pipe, is the same. Either the displacement is 0 or pressure change is 0. The frequency, nth frequency or nth harmonic frequency comes out to be n times V over 2L for the length L of the pipe or the string. And the only difference is in terms of V, V for the string is nothing but square root of T over mu, and V for the pipe is nothing but square root of the bulk modulus divided by the density times the gamma factor, which comes because we consider adiabatic expansion of the air column. So, this is what it is. Now, similarly, I can also consider now the case of closed string. Similarly, I can consider the case of closed pipe, in which case delta P at this end will not be equal to 0, whereas delta P at the open end is 0. This, recall, is exactly the same case as the string, where string left end is tied. Okay, left end of the string is tied and the right end is being moved with some amplitude A. Remember, in this case what happened is that I still can take my y x to be some amplitude sine of k x cosine omega t. Sine k x is chosen because it automatically gives me 0 at x equals 0. However, k L sine of it is not 0. In fact, it is maximum. In that case, we learned that K L should be equal to 2n plus 1 pi by 2, and we got our answer for K. K was 2 pi over lambda times L is equal to 2n plus 1 pi by 2, and we cancel pi on both sides, and we get lambda equals 4L over 2n plus 1. That was the case of the string. Exactly the same thing is going to happen in the present case. Here is a string which was tied and this end was vibrating. So, I could have modes where I had either lambda by 4 or 3 lambda by 4 and so on. Exactly in the same manner, if I have a pipe which is closed on this x equals L and open at x equals 0, I would have delta P as a function of x and t equals some large value A amplitude sine k x cosine of omega t with k x such that x equals L, that is it becomes K L is equal to 2n plus 1 pi by 2. So, it gives me exactly the same answer as that for a string which is tied at one end and is being shaken on the other side, and this again gives me 2 pi over lambda L equals 2n plus 1 pi by 2, and I can cancel a few terms. So, pi cancels and I get lambda equals 4L over 2n plus 1, and therefore, the frequency nu n is going to be V over lambda, which will be equal to 2n plus 1 over 4L times V, or I can write this as n plus a half V over 2L. Again, V over 2L is the fundamental frequency and rest are higher harmonics. So, you see this is exactly the same case as in the case of string, except that the velocity now is going to be not square root t by mu, which was the case for the string, is going to be gamma square root b by rho. So, let me write this. The velocity now in this case is given to as gamma square root of b by rho, where b is the bulk modulus, rho is the density, and gamma is the Cp over Cv for the gas. So, the only thing that changes is the velocity, rest because of the boundary conditions is the same. Now, in the previous lecture I had also given you the physical interpretation of the modes in a string. In fact, I should write on a string or in an air column. It is exactly the same. Now, when I have this air column, the pressure is 0 at the ends and in between it varies. So, it could vary like this, maximum in the middle, and then it keeps changing with time, or it could vary being 0 at the ends and in the middle it would be like this, and so on. So, what you have is either lambda by 2 exists or lambda could exist. This is actually 3 lambda by 2 and so on. So, the wavelengths that can exist are such that n lambda by 2 is equal to L or lambda equals 2L over n, exactly the same answer as before. And you can do similar physical interpretation for the pipe closed at one end. Now, one difference is there between the string vibrations and air column vibrations, and this is known as the end correction. What is that? I just want to remind you that when we took this open ended pipe or a pipe closed at one end, what we said was right at the end of the pipe delta P is 0. And therefore, the length that we took for the wavelength was exactly the length of the pipe, which is the same answer for this string also. What happens in the air column case is that the node or the delta P 0 does not come exactly at the end of the pipe, but slightly outside, and this distance happens to be 0.6 times r. You can take it to be an experimentally established fact. Similarly, if the pipe is open at both ends, the node on both sides occurs as at a distance of 0.6 r, where r is the radius of the pipe. So, effectively the length for open ended pipe would be equal to L plus 1.2 r. So, let me write this in capital effective. And similarly, effective length for a pipe closed at one end will be equal to L plus 0.6 R. These are the corrections that you got to make in the length, and it is this length, effective length, that you are going to put in the formulas. Otherwise, the formulas remain exactly the same. Velocity is that the velocity equal to the velocity of sound in the air, which is gamma square root b by rho, and rest of the things remain the same. We have discussed so far the superposition of two waves of the same frequency and paid attention to the waves which are traveling in opposite directions, and that gives rise to what we have discussed so far, the standing waves. I now want to discuss superposition of waves that have slightly, very slightly different frequencies. What we mean by that is, suppose one frequency is nu 1, the other frequency is nu 2, then nu 1 minus nu 2 magnitude is much less than either nu 1 or nu 2. For example, I could have nu 1 equals 500 hertz and nu 2 equals 502 hertz. So, the difference is really small. What happens in that case? And that case gives rise to something called the beat phenomena. And I like to discuss that. So, for that, let me consider one wave which is traveling in one direction, let us say to the right, and it is given by y x t equals some amplitude a sine k 1 x minus omega 1 t. Another wave which is slightly different in frequency, very slight, also traveling in the same direction, and I have y x t, let me call this y 2, the first one y 1, is equal to some amplitude b sine of k 2 x minus omega 2 t. And I stand at a certain point x. So, we stand at a point x equals x naught, and for simplicity let us take this to be 0. So, that my whole thing simplifies and I have y 1 t at that point is equal to minus a sine omega 1 t. Let me also take it plus, it does not matter, because finally I am going to look at the intensity, and y 2 t is equal to b sine of omega 2 t. Now, these two waves are going to superpose, and therefore, the net displacement at that point is going to be given as y 1 t plus y 2 t is equal to a sine omega 1 t plus b sine omega 2 t. So, when these waves superpose, I have y t at that point where I am standing is equal to a sine omega 1 t plus b sine omega 2 t. And this will give rise to phenomena of beats. It is easiest, beats can be understood easily if we take A equals B. That means I am taking the amplitude of the two waves to be the same. If they are different, I'll work that out also a little later, but in this case what I'll have is y t is equal to A and in the brackets sine omega 1 t plus sine omega 2 t, which I can write as 2A sine of omega 1 plus omega 2 over 2 t times cosine of omega 1 minus omega 2 over 2 t. Let us check that first. If omega 1 equals omega 2, then I get my answer as y t equals 2A sine of omega t, which is correct. Now, interesting thing happens when omega 1 is not equal to omega 2. So, let us consider the case when omega 1 is not equal to omega 2, and let us take omega 2 to be equal to omega 1 plus some delta omega, where delta omega is much less than omega 1. Then I can approximately write my y t is equal to 2A sine omega 1 plus omega 2 can still be taken as just omega, or if I want to be very precise, I will write this as sine omega plus t times cosine of omega minus t, where omega plus is omega 1 plus omega 2 over 2, which I can write approximately as omega 1, and omega minus is equal to omega 1 minus omega 2 magnitude. For cosine it does not really matter, divided by 2. So, what I have is that y t is equal to 2A, which is some amplitude sine of omega plus t and cosine of omega minus t. Omega minus is much less than omega plus. So, if I were to plot it as a function of time, the first term omega plus t is very high frequency. So, that is going to vary very fast. The time period t plus, which is 2 pi over omega plus, is much shorter than t minus, which is equal to 2 pi over omega minus. And if I multiply this by omega minus is much slowly varying. So, the second term varies very slowly, and then it will go down. So, if I multiply the two terms right here, I will show this. If I multiply the two terms, what I am going to get is something like this. Becomes small again, and then it will pick up again. This term is cosine of omega minus. In fact, what I have multiplied by is sine omega minus. This is sine of omega minus t. So, you have learned one more thing. If I multiply sine omega minus t and sine omega t, how do they look? This is sine omega plus t. Let me correct myself for the other function, which is a sine of omega plus t cosine of omega minus t. If I were to plot cosine term, it will be something like this. So, sine omega t is going like this, cosine omega t term would be 1 here, and then slowly go to 0 and go like this. So, the product is going to look like large, it will become small, and it will pick up again, become small, and it will pick up again. So this is going to be a profile like this. This is the product sine omega plus t cosine omega minus t. So what you notice is this is as a function of time, that as a function of time the vibration is increasing in amplitude and decreasing in amplitude slowly, and you can feel it. Why you can feel it? Because this is happening at a much smaller scale than the vibration sine omega plus t itself. So if there are two sound waves of slightly different frequencies, and if I stand at one point and hear them, what I am going to hear is that suddenly the loudness of the wave is going to, loudness of the sound is going to be large, then it will go down, it will come up again, it will go down, it will come, and this is known as the phenomena of beats. There are these beats taking place. And what is the frequency of beats? Now notice that my amplitude y x t is 2a sine of omega plus t cosine of omega minus t. In the case of sound, it is going to be delta p x t is going to be some large pressure p sine of omega plus t cosine of omega minus t, and the energy that you are going to get is going to be proportional to delta p square. What happens is this frequency is omega 1 minus omega 2 divided by 2. So the pressure difference is going to be large, small again, large, small again, but you are going to hear a loud sound at this point where I am drawing a vertical blue line, at this point, at this point, and this difference is twice the frequency itself. This is half. This time period is t by 2, t minus by 2, which is 1/2 of 2 pi over omega minus, which is 2 pi over omega 1 minus omega 2 magnitude. So the beat frequency which is how many times you are going to hear the sound go up and down, is going to be equal to omega 1 minus omega 2. Because every time the amplitude goes up, whether it is on the negative side or the positive side, you are going to hear a loud sound. So beat frequency is equal to the difference in the frequency. Keep in mind that the moment omega 1 becomes equal to omega 2, beat frequency is equal to 0. Now you may ask, I took A, the amplitude, to be the same for both waves. This was to give you an idea as to what happens. If the amplitude is different, that means I have sine omega 1 t plus b sine of omega 2 t. I could write this as A plus b divided by 2 sine omega 1 t plus A minus b divided by 2 sine of omega 1 t plus A plus b over 2 sine of omega 2 t minus A minus b by 2 sine of omega 2 t. So I am going to get this equal to A plus b by 2 sine of omega 1 t plus sine of omega 2 t plus A minus b by 2 sine of omega 1 t minus sine of omega 2 t, and this is going to give me A plus b by 2 sine of omega plus t cosine of omega minus t plus A minus b by 2 cosine of omega plus t sine of omega minus t, and in fact, I should put a minus sign here. So, you notice again this is a superposition of two waves of different amplitudes, but both showing phenomena of beats. So, you are again going to hear beats, and what I like you to do is try to plot this as a function of time and see how many beats are you going to hear. Is it exactly omega 1 minus omega 2 or something more happens, but the idea is now clear. Idea is that when you mix two waves which have slightly different frequencies, the amplitude of the superposition varies with time very slowly, and you hear amplitude going up and coming down, and this is the phenomena of beats. And finally, in these lectures on oscillations and waves, we discuss something called the Doppler effect. What it concerns itself with is, suppose we have a source of waves and it is moving with some velocity v source, and I as an observer observe it from a certain point. Now, observing means I could, the most common thing that I could do is that the source is a sound source and I hear it, the sound standing some point. So, this is moving with V source and I am standing at an angle from the direction in which it is moving. Or it could so happen that the sound source is stationary and I as an observer am moving, or a combination of the two. In that case, what is seen is that the frequency observed and in this case, in the case of sound, when I say frequency observed, it is the frequency heard is different from the frequency emitted by the source, and this is known as Doppler effect. What we are going to study now is how the observed frequency or the frequency that we hear, how much does it differ from the frequency that is being emitted by the source. We are going to confine ourselves to the cases where theta is 0. That means that the source and observer are right along the line of movement of the source or the observer. They are not at an angle from it. So, let us consider these cases one by one. Now, case 1 I am going to study is source moving towards the observer. So, let us take the source and here is the observer. It emits a wave at a particular frequency, let us call it nu 0, or I will not put nu 0, I will just call it nu, because I will otherwise get confused with when I put O for the observer. So, this is some frequency nu. So, let a particular wave be emitted from here. Let us take a particular point, the maximum displacement. So, when maximum displacement is given out, it travels towards the observer and the distance between two maximum displacement is lambda, right, which is given by V divided by nu, where V is the speed of wave. This is when the source is stationary. Now, let us see what happens if the source is moving. So, here is the observer, here is the source, and it gave out a particular maximum. This maximum starts traveling, and after a time period t, it again gives out a maximum. So, this maximum is traveling towards the source or towards the observer. By the time the next maximum is given out, in the case of stationary source, this distance was lambda. Now, this distance is going to be reduced because the source has moved, and this is going to be reduced by velocity of the source times t. Okay. If I make it on the left hand side, so this maximum traveled or distance lambda, and by the time the next maximum was emitted, the source has moved by a distance of v source times t, because it emitted that after time t. So, effectively lambda has become this one shown by purple, which is lambda prime equals lambda minus v source times t. So, the lambda that the observer is receiving is lambda prime, which is equal to lambda minus v s t. So, the frequency that person is going to hear, which I will call nu 1, is going to be the speed of wave divided by lambda prime, which is v divided by lambda minus v s t. Let us write everything in terms of the original frequency. So, v is v, lambda is nothing but v divided by the frequency minus v s, t is 1 over the frequency, which is equal to v divided by v minus v s times the frequency. So, the frequency at which now I hear these maxima of the wave coming to me is slightly larger. So, what we have deduced is that if there is a source which is moving towards an observer along the line of the line which is between the source and the observer, then the frequency that the observer hears is v divided by v minus v source times nu, which is greater than nu. By the same logic, if this fellow source was moving the other way along the line joining the observer and the source, then nu would be v over v plus v source times nu, which is less than nu. So, I am going to hear either a higher frequency or a lower frequency. This you see very often when you are standing near a railway gate. If the train is approaching you and blowing a whistle, you hear much higher frequency, and it passes through you and goes away from you, you hear the frequency which is lower. The way you feel it is that the quality of sound changes. So, this is case 1. Case 2 is when an observer is moving towards the source. So, in this case again, here is the source, and this observer now is moving towards the source. So, here are these maxima which are being emitted at regular intervals of time difference t, and the distance between them is lambda. But because this observer is moving towards the source, he or she is going to hear or see the difference between them to be slightly shorter, and therefore, higher frequency. Let us see how much shorter does he see them to be. So, we will apply the same logic as before, and what we are going to see is, here is the source and there is this maximum which is moving towards the observer. Here is another maximum which is also moving towards the source, both by velocity v, and the observer is moving towards them with velocity v0. The difference between them is lambda. So, question we are asking is, what is the effective distance that the observer sees or feels between the two maxima. And I need one more thing for this, is that these two are emitted at time interval t. For this, what we are going to consider now is, let the first maximum be emitted at time t1 and the second one at time t2, so that t2 minus t1 is equal to t. Now, let the observer here the first maximum at t1 prime and second maximum at t2 prime. So, what is going to happen is, here is this wave coming, these are the maxima, and at t1 prime this observer is here and the observer is moving in this direction. So, you are going to have t1 prime plus lambda divided by v plus vo, because the relative speed between this maximum moving this way with speed v and observer moving with speed vo is v plus vo, and they have to travel a distance of lambda before the observer hears the second maximum is going to be equal to t2 prime. So, the observer hears the second maximum at t2 prime. So, the time interval or time period felt by the observer is equal to t2 prime minus t1 prime, because this is the interval in which he heard the two maxima. So, t2 prime minus t1 prime from the equation above comes out to be lambda divided by v plus vo, and this is t prime, which is 1 over nu prime, where nu prime is the frequency that the observer feels, and this is equal to lambda divided by vo plus v observer, and let me write this as v over nu times v plus v observer, and this immediately gives you that nu prime is equal to v plus v observer divided by v times nu, which is greater than nu. So, observer moving towards the source also hears a higher frequency, because the maxima are coming at a faster rate. So, what we saw is that if a source is stationary and an observer is moving towards it. Because the observer sees maxima coming at a faster rate, he hears a new frequency, which is V plus V observer over V times nu. Of course, if the person is moving away, then nu prime would become V minus V observer over V nu, which is less than nu. So, what we have learned so far is source, observer moving towards each other, moving away from each other, and so on. We can combine all these and write that nu prime is going to be equal to V plus or minus V observer divided by V plus or minus V source times the source frequency nu, where VO plus sign is for observer moving towards the source, and plus Vs is for source moving away from the observer, and you can fill in the rest of the combinations. An interesting variation of this problem comes when we consider a source moving towards a wall and the source hears his or her own sound. So, what happens in this case is that the wall first receives the frequency from the source as source moving towards observer. So, in this case, if the source frequency is nu, the wall is going to receive a frequency nu prime, which is going to be V divided by V minus Vs times nu. And this frequency is emitted back or reflected by the wall, and now the person hearing it becomes the observer. So, it is now the observer moving towards the source, and this nu double prime is therefore is going to be V over V minus Vs nu, which is the frequency coming towards the person, times V plus V source divided by V. So, this V cancels, and the person is going to hear nu double prime, which is equal to V plus Vs divided by V minus Vs times nu. A variation of this could be that the wall is moving towards the person, towards the source, and source is just standing. In that case also you can show that this is going to be V plus V wall divided by V minus V wall times nu. That is the frequency that person is going to hear. So, let me finally conclude the lecture by stating that we have considered frequencies of an air column in a pipe. Pipe could be closed at one end or open at both ends. We have also considered the phenomena of beats in which two waves of roughly the same frequency superimpose, and third, we have considered Doppler effect in which the frequency that we hear, because the source or observers are moving, are different.